In this lecture, we are going to talk about a different method of solving the explore-exploit dilemma, known as the optimistic initial values method. The optimistic initial values method is an extremely simple modification of the purely greedy method. In other words, we don't even need any concept of epsilon and random exploration. The way it works is this. As you recall, in our measurement of the sample mean, we update our current estimate based on our previous estimate. Our initial estimate is 0 to ensure that all the math works out and we get exactly the sample mean. The optimistic initial values method says this. What if, instead of initializing the initial estimate to 0, we pick a really large value and include that in the estimate of the sample mean? In this way, we're not really estimating the mean per se, we're actually overestimating the mean. Just to be clear, let's look at some pseudocode for how this would work. First, we initialize all our bandits to have their initial means to be very large values. As a side note, they must be finite, because if you pick infinity, then you can't do any further calculations with it. Infinity plus anything is still infinity. Then, inside our experiment, instead of doing any kind of random exploration, we simply choose the bandit with the highest estimated mean. Since we initialize this value to be very large, this isn't necessarily close to the true mean, but rather it's an overestimate of the true mean. The next step is to consider the part of the code where we choose the bandit. As I mentioned earlier, we don't need to choose anything randomly. We can just act in a greedy manner and choose the bandit with the largest estimated mean. The question is, why does this even work? Let's think about it. Remember that our goal is to balance exploration and exploitation. Exploration is the same as saying you want to collect lots of data. So what happens with our estimated mean? If it's early on in our experiment and we haven't collected a lot of data yet, then our estimated mean will be very large. Not because the true mean is large, but because we set the initial value very large, and it has yet to converge to the true mean. On the other hand, after we've collected lots of data, the estimated mean is going to get smaller and smaller and smaller until we stop choosing that bandit. Remember that the sample mean is the arithmetic average of all the samples you collected. So even if you have one extremely large value, its effect is going to disappear when you have 1,000 or 10,000 samples. One interesting question to ask yourself is this. In epsilon greedy, we saw that our estimate of the mean for each bandit converged to the true means. Do you think this will happen with the optimistic initial values method? I'll let you think about this for a few moments. Please pause the video if you would like to think about the answer on your own. In fact, the answer is no. Remember that, since we're using the greedy method, there's no guarantee we'll collect a large number of samples for any single bandit. What will happen is, if the estimated means for the suboptimal bandits go below the estimated mean for the optimal bandit, we will stop exploring those suboptimal bandits entirely, and that's because we're being greedy. So the only result we can expect is that those estimated means are below the optimal bandit's estimated mean, not that they have converged to their true means. In fact, we can't even expect the optimal bandit to have a good estimate of the true mean, because the initial value could have been so high and the number of trials low enough that the estimated mean is still an overestimate by the end of the experiment. The next question I want to address is, what is the role of the initial value? The intuition is hopefully clear by now. It's that if you set this value very high, then it'll cause the algorithm to explore because the greedy method will believe that the bandit has high mean reward, even when it doesn't. To determine the role of the initial value, you have to ask the question, how high? So if you set the initial value extremely high, then you're saying, I want more exploration, because it's going to take more time for the estimated mean to go down towards its true mean. If you set the initial value only a little high, then you're saying, I want just a tiny bit of exploration, because it's going to take much less time for the estimated mean to go down towards its true mean. So the initial value is then a hyperparameter that controls the amount of exploration. High initial values mean more exploration, and smaller initial values mean less exploration. But even when you set a small initial value, it still should be greater than the typical set of rewards you would get in order for this algorithm to work.